Hi everyone, today the final video in the amount of substance topic, looking at balanced equations and all the related calculations. So the first thing to look at is the type of equations that we can see. Now the kind of equation that you'll be very used to is the full equation, sometimes called the stoichiometric equation. These are balanced equations that show all the reactants and the products in a reaction. And we could write them down as words, but they're normally written as the chemical symbols. And when we talk about the stoichiometry, what we mean is the ratio of the symbols. So if we have 2a plus 3b, the stoichiometry of that is 2 to 3. It's the mole ratios, essentially. The other type of equation is something called an ionic equation. Now this is a simplified version of the full equation. It's often made by starting with the full equation and cancelling things out. And it's created by considering the ions present in a reaction. And so we're only going to consider the ions that actually take part in a reaction. So this often leaves us with the simplest form of an equation for a given reaction. Now something that we don't necessarily always put into our ionic or full equations when we write them, but we really should, is the state symbols. So we have an S for solid, an L for liquid, a G for gas, and an AQ showing an aqueous solution, meaning that we've dissolved it in water. And these can also be added, but they're essential for ionic equations, and we'll see why in a moment. But in general, whether we're writing an ionic equation or whether we're writing a full equation, we have to make sure that they're balanced. We have to make sure that the atoms and the charges balance on both sides. So, an example. Let's say we have this example where we've added phosphoric acid, H3PO4, to barium hydroxide. Now this is essentially an acid-base reaction. Barium hydroxide is a base, and phosphoric acid is an acid. So it's an acid-base reaction, a neutralization reaction. So we're going to form our salt plus water. The salt that we form is barium phosphate. We have to make sure that our charge is balanced in this. So barium is a 2+ ion. The phosphate anion is a 3- anion. We started with H3PO4, so 3 lots of plus means that our PO4 ion is a negative ion, 3- ion. So to make those balances, we have to have 3 bariums and 2 of the phosphate anions to make Ba3PO42. Plus water, because it's a neutralization reaction. So the first thing that we always do is we balance and we add our state symbols. So the easiest way to balance these kind of equations is to look for kind of unusual atoms. Often there's hydrogens, often there's waters in most chemical equations. But in this example, we also have phosphorus and we have barium. So the first one I would look at is look at the barium. We have Ba3 on the right-hand side. Therefore, we're going to need 3 bariums on the left-hand side. So that balances those up. We can then look at the phosphorus. Over on the right-hand side, we have 2 phosphoruses. So therefore, we need to put a 2 in front of the thing that has the phosphorus on the left-hand side. And so we put 2 in front of the phosphoric acid. So we've immediately balanced up our bariums and we've immediately balanced up our phosphoruses really, very easily. We haven't really had to do anything. Just looked and put a number in front. And so it's always a good trick to leave the hydrogen and oxygens until the end, because these will probably be the more complicated ones to look at. So if we then look at balancing our oxygens or our hydrogens, let's look at hydrogens. On the left-hand side, we now have 6 from the acid, and we also have 6 from the barium hydroxide because we have OH2, so 2 hydrogens normally, and 3 times that is 6. And so total we have 12 hydrogens, so if we have H2O on the right-hand side, 12 divided by 2 is 6. We need 6 waters. And also we can look at the oxygens, and you can double check for yourself to find that those are balanced as well. We're then going to put our state symbols in. So the phosphoric acid will be a solution of phosphoric acid, aqueous solution. Remember that aqueous just means that the solvent is water. So water is a polar molecule, and so it's good at dissolving other polar compounds. So the key thing really is that if we dissolve the phosphoric acid up in water, we have a solution of it. It doesn't actually exist as H3PO4, it exists as the ions in these solutions. And this will be important for the ionic equation. So aqueous for the phosphoric acid. The barium hydroxide will also be an aqueous solution, AQ. The barium phosphate will also be aqueous, right? It's an ionic salt, but it's in water, so it will be dissolved up, aqueous. And then finally, the water is liquid. So we've balanced our equation and we've put our state symbols in. That's our full equation, our stoichiometric equation. If we wanted to look at our ionic equation, the really key thing we're going to do is we're going to break down the ionic species. And typically, we're going to break down only the aqueous species. So we're not going to bother breaking down the gases or the liquids into ions. So that means we break up our phosphoric acid, we break up our barium hydroxide, and we break up the barium phosphate. So the key thing here is to note that we have to make sure that we have the right number of things. So by breaking up phosphoric acid on its own, we would end up with 3 lots of H plus and 1 lot of the PO4 3 minus, the phosphate anion. However, because we have 2 lots of H3PO4, it's why it's really important to start from a balanced stoichiometric equation. We have 2 lots of phosphoric acid, so really we have 6 H plus and 2 PO4 3 minus. We can do the same thing with the barium hydroxide. We have 3 lots of the barium 2 plus ion, 6 lots of hydroxide anions, and then on the right hand side, break up the salt, 3 lots of the barium 2 plus ion, 2 lots of the phosphate anion, and then the water we leave untouched because that's a liquid, it's not an aqueous thing. It doesn't exist as ions, it exists as H2O, covalently bonded. Now what we do is we just cancel anything on both sides that exists on both sides. So we have 3 bariums, 2 plus ions on both sides. They get cancelled out. We have 2 phosphate anions on both sides. They get cancelled out. And what that simply leaves us with is 6H plus 6OH minus to 6H2O. And we can simplify even further by removing the 6's. And so essentially we have a proton plus a hydroxide anion giving us water, a neutralization reaction. Now, of course, we know that generally this is a neutralization reaction. We've seen that from the full equation, but this is a way to get to the actual simplest form of that equation, which is H plus and OH minus forming water. Now, the barium and the phosphate anion are known as what we call spectator ions. They are ions that are there, they're involved in the reaction, involved in the equation, but they don't actually get involved in the reaction. They're not in the actual ionic, simplest equation, the ionic equation. So, using these balanced equations, and normally a balanced stoichiometric equation, there's lots and lots of things we can work out. We can work out reacting masses, we can work out volumes of gases, concentrations and volumes for reactions in solution, percentage atom economies, and percentage yields are just some examples. So we're going to go through lots and lots of examples in the next few slides. So an example might look like something like this. So we have our equation, and the question might say to you that we've added 7.5 centimeters cubed of something called ethanol chloride to 10 grams of 2-hydroxybenzoic acid. What is the maximum amount of product that we could form? Now, this reaction is actually the reaction to form aspirin. So we take ethanol chloride, react it with 2-hydroxybenzoic acid, this forms aspirin and HCl. Now, the important thing in questions like this is that we're just working out the maths of it. So it doesn't matter if we see an equation that we don't recognise or chemistry that we don't recognise. It might look a bit complicated, but we don't have to actually understand how the equation works. We don't have to actually understand the actual mechanism for this or how this works. We just need to use the numbers to work out the maths. So, again, as I've said in previous videos, even if you're a bit confused what to do, use the data the question gives you in some way. So the first thing that we can do is we're given the mass of the 2-hydroxybenzoic acid. We also have the formula, so we can work out an MR, and this means that we can work out the moles of the 2-hydroxybenzoic acid. So the MR, remember, we just add up our atomic weights of all the elements involved. So we have 7 carbon atoms, so 7 times 12.0. Remember that AR and MR values are always given to 1 decimal place. 6 hydrogens and 3 oxygens give us a total MR of 138.0. And so that means that our moles, remember that our equation for moles is mass over MR, we take our 10 grams, we divide by 138.0, and we end up with 0.072 moles of our 2-hydroxybenzoic acid. Now the question said that we had 7.3 centimeters of ethanol chloride, and it told us that that was an excess of that reagent. Now sometimes it won't tell you, in which case you need to work out the moles of both. So for example, for the ethanol chloride, it will also have to give you the concentration, of it in order to work out the moles. In this case, we're told that it's the excess reagent. This is really important because of something called the limiting reagent. Whatever the mole value is smallest, whichever one is smallest out of our reagents, is the limiting reagent. It is the one that is going to limit how much product we can form. It is the one that's there in the smallest amount, and so is the thing that really limits how much product we can form. And so in this question, we don't necessarily have to worry about that because we can only work out the moles of the 2-hydroxybenzoic acid. But if it was a question where you could work out the moles of either, do both, see which one's the limiting reagent, and that is the number that you use in the calculation. So we know our moles of 2-hydroxybenzoic acid are 0.072. We then use the fact that we have a 1-to-1 mole ratio. This is why it's really important to make sure our equation is balanced. Now, the equation that's given to us in the question is already balanced. Sometimes they will get you to write the equations out yourself, and even if the equation is written in the question, it's always good to double check that it's balanced straight away. And in this case, it is. So everything is in a 1-to-1 mole ratio, and that means that the amount of moles we have for our 2-hydroxybenzoic acid must also be the same amount of moles for the aspirin, because it's a 1-to-1 ratio. So we're going to have to rearrange our equation to work out the mass. Remember that mass is moles times the MR, so we need to have the MR for aspirin. Again, just add up all of the atomic weights of all of the elements involved, and when we do that, we get an MR of 180.0, remember, to 1 decimal place for aspirin. And then our mass is the MR times the moles, so 180 times 0.072 gives us 13 grams of aspirin. Now what this means is this is the theoretical yield, the theoretical maximum 100% yield of aspirin. If I didn't lose any product in doing this reaction, the maximum that I could make is 13 grams if I started with 10 grams of 2-hydroxybenzoic acid. Now, I'll see in a few slides this quantity called the percentage yield, but essentially the percentage yield is, well, how much did I actually make divided by how much have I theoretically made. And so if I only made 11 grams, then we can work out the percentage that we truly made being 11 divided by 13, and 84% is the answer. We'll see in a few slides a few more examples of percentage yield. Another example is this question here. We have magnesium reacting with hydrochloric acid to produce magnesium chloride and hydrogen. And the question states to calculate the volume of hydrogen gas produced at 25 degrees Celsius and 100 kilopascals. So the first thing is to always check that the equation is balanced. In this case, it isn't balanced, so we have to do some balancing. We have 2 Cl's on the right-hand side from the magnesium chloride, so we need to put a 2 in front of the HCl, and then it's balanced. So the question gives us that we have 4 grams of magnesium, and our HCl was 100 centimeters cubed of a 1 mole per decimeter cubed solution. So we've checked the equation is balanced. We're going to use the data in the question so we can work out the moles of magnesium and we can work out the moles of HCl. So remember, for moles of magnesium, it's a solid moles question, so mass over MR. So the grams of it, which is 4 grams, the mass, divided by the MR of magnesium, or the AR of magnesium, technically the atomic mass of magnesium, 24.3, gives 0.165 moles. If we do the same thing for HCl, we use this as a solution moles calculation, so we have to use that moles is concentration times volume. But remember, when we do this kind of stuff in solution, we have to remember that concentration is moles per decimeter cubed. Volume here is given to us in centimeters cubed, so we have to convert the 100 centimeters cubed into decimeters cubed by dividing by 1,000. If you're not sure with the unit conversions, go back to one of my previous videos on the solution moles calculations and we'll see some unit conversion. So we put the numbers in and we find that we have 0.1 moles of the HCl. Now this is where it's really important to know about our limiting reagent, and the reason for this is because we have less moles of the HCl than we do of the magnesium. Essentially the magnesium is in excess. So we have to use the 0.1 moles in our calculations, because that is the limiting reagent. That is going to be the one in the smallest amount that limits the maximum amount of products we can get. So using the mole ratios, and typically in these questions we always have to get to a point where we look at the mole ratios, we know from our mole ratios that there are 2 moles of HCl, reacting with 1 mole of magnesium to produce 1 mole of magnesium chloride and 1 mole of hydrogen. So the ratio of HCl to hydrogen moles is 2 to 1. And so the moles of the hydrogen is actually the moles of our HCl divided by 2, 0.05 moles. Now we have the moles, we have the temperature, we have the pressure, so we can work out the volume through the ideal gas equation. So PV equals nRT. We want to work out the volume, so divide both sides by the pressure. Volume is nRT divided by P. And remember that our ideal gas has very specific units. If you're not happy with these units, go back to the ideal gas video and look again at the unit conversions. But our volume is always going to be in meters cubed, temperature in Kelvin, and pressure in pascals. So we're going to put our mole value in, 0.05, times it by the molar gas constant, 8.31, times it by the temperature, which we were given as 25 degrees Celsius. Remember, we have to add 273 Kelvin to get to the Kelvin value, which is 298. And then we have our pressure, which must be in pascals. We were given it in kilopascals, so we're going to times by 1,000, or times by 10 to the 3. And when we put all those numbers in, we end up with a volume of 4.1 times 10 to the minus 3 meters cubed. And again, as we've seen in lots of other of these videos, we have to make sure our significant figures are consistent. We can only give it to the minimum number of significant figures in the question. The 4 grams is 2 significant figures, 100 centimeters cubed is 3 significant figures, and 1.00 mole per decimeter cubed is 3 significant figures. So we have to give our answer to 2 significant figures, 4.1. So another type of question we might see is a titration question. So remember that in our titration, we're going to have typically an acid and a base, ending up forming our salt and water. It's a standard neutralization reaction. And typically we're going to know the concentration and volume of one and only know the volume of the other, not know the concentration of one of the partners. So we might have a flask that contains our alkali and our indicator. We've measured out a specific volume of that, in this case 40 centimeters cubed, of our sodium hydroxide. We have a burette with our acid in. Now the acid we know the concentration of, 0.2 moles per decimeter cubed. And what we're going to do is add this until we see the colour change of our indicator. And you can see in the picture here that this is a pink indicator. This is normally phenolphthalein. And we would see this colourless to pink change when we hit the neutralisation point, when just enough base has been added or just enough acid has been added to neutralise, or vice versa. So we're told that 26.5 centimetres cubed of the HCl is enough to neutralise the sodium hydroxide. And we're asked to find what is the concentration of that sodium hydroxide solution. So the first thing is to write the equation. NaOH plus HCl goes to NaCl plus H2O. Include your state symbols. The NaOH is aqueous, the HCl is aqueous, the NaCl is also aqueous, and the H2O is a liquid. Check that it's balanced. In this case it is, so we don't have to do anything to it. And then use the data in the question. So we've got the concentration, we have the volume for the HCl, so we can work out the moles. This is a solution moles question, so we're going to do N equals CV. So remembering, of course, to change the volume that's in centimeters cubed into a decimeters cubed, so dividing by 1,000. So we put the numbers in, 26.5 divided by 1,000 times 0.2, and we get 5.3 times 10 to the minus 3 moles of our HCl. Now we look at our mole ratios. It's a 1-to-1 ratio between the HCl and the NaOH. So therefore the moles of sodium hydroxide are exactly the same, 5.3 times 10 to the minus 3. And then to work out the concentration, we just rearrange our equation. So N equals CV, we want to find concentration, divide both sides by the volume. The concentration is the moles divided by the volume. Remember, of course, that our volume, we want it to be, well, our concentration is going to be in moles per decimeter cubed, so we need our volume to be in decimeter cubed. However, the volume in the question we were given is in centimeters cubed, so we have to convert, this time by dividing by 1,000 again, or we can move that up to the top of the equation, times by 1,000, it's the same thing. And so we end up with our 40 centimeters cubed divided by 1,000. For our volume, moles is 5.3 times 10 to the minus 3. And you put those numbers into the equation, and we end up with a concentration of 0.133 moles per decimeter cubed. And here we can do it to 3 significant figures because we have 3 significant figures for everything in the question. Now, two things that we haven't really talked about. The first is atom economy, and this is something that is found directly from the balanced equation. So the atom economy, essentially, it tells us in theory how many atoms are wasted in a reaction. So let's say we have a reaction of A plus B goes to C plus D. If the actual product that we really want is C, not D, D could be a side product like water, for example, what we're going to do is we're going to see, well, how many atoms from A and B actually go into the desired product of C. And so the way we work this out is we take the molecular mass of the desired product and then we divide it by the sum of the molecular masses of the reactants. So we work out what is the molecular mass of reactant A, what is the molecular mass of reactant B, add them together. We work out what the molecular mass of our desired product C is, and we do the mass of C divided by the mass of A plus B, times by 100 to get a percentage. So an example of this atom economy could be for the following reaction. We have CH3CH2OH, ethanol, reacting with CH3COOH, ethanoic acid. And this produces this ester here, CH3COOCH2CH3, ethyl ethanoate, plus water. Now again, if it's an unusual reaction that we don't recognise, we don't need to worry about that. We're not interested in the actual chemistry, we're not interested in the mechanism or how this works, but we're simply interested in dealing with the numbers. And so we're going to work out our atom economy. Our ester is the useful product. We're going to take our molecular mass of that useful product divided by the sum of the molecular masses of our reactants. Remember, to work out the molecular masses, we just sum the atomic masses of each element involved. And when we do that calculation, times it by 100, we find that our atom economy is 69%. So that means that 69% of our atoms from the reactants have gone into the useful product. Another way to think of it is that 31% of those atoms get wasted going into the water. Now, atom economy is a 100% theoretical thing. It doesn't tell you anything about the yield of a reaction. You could have a very, very high atom economy reaction that's very low yielding. Likewise, you could have a very low atom economy reaction that's very high yielding. So the percentage yield, as we'll see on the next slide, is the actual practical sort of how much you get out of it. The atom economy is the theoretical side of it. So percentage yield tells us about the practical efficiency of a process. How much is lost due to actually practically getting the product, or of a result of reactions that are equilibrium reactions. They don't actually go fully to completion. So this could be reversible reactions that don't fully go to completion. They exist as an equilibrium. Or it could be losses such as when you transfer a solution into another solution, you're not going to be able to transfer 100% of that solution because some of it will always, droplets will always still be stuck to the beaker. You can also have stuff being lost on filter paper, for example, if you're filtering it, things like that. So any kind of practical process where you're going to lose a bit of your product. And so the mathematical equation for this is our percentage yield is the actual mass that we get from our reaction divided by the theoretical mass. Now, earlier on we did a question where we worked out what was the theoretical mass of aspirin that we could produce from a certain mass of our reactant. That's our theoretical mass. We're not thinking about actually how in reality we obtain that product, just simply based off how much reactant we have. Theoretically, what's the 100% yield? What is the 100% theoretical mass we can get? And we times that by 100. We can also do it with moles because this is the percentage, so as long as what we have on the top and the bottom is exactly the same, that's fine. So we can use it by doing the actual mass divided by the theoretical mass, or the actual moles divided by the theoretical moles. And so back to the same reaction that we saw here, making this ester. If we said that, say in a previous question, we've calculated that the theoretical mass of ethyl ethanoate is 7.2 grams, and we actually measure out in the lab when we've got it that the real mass obtained was 5.9 grams, what's the percentage yield? And so simply we take our actual mass, divide it by our theoretical mass, times 100, and our percentage yield is pretty good here, it's 82%. So we've only lost 18% of our product. So, time to have a go at some questions, and there's quite a few questions to have a go at today. We're going to find some ionic equations, calculate atom economies, and then work out some yields. So if you want to have a go at the questions, pause the video, and the answers will be on the next slide. So for the first question, we had the reaction of sodium carbonate reacting with sulfuric acid to produce sodium sulfate, carbon dioxide, and water. To find the ionic equation, remember that we have to, first of all, balance our equation. Now already, this equation, if you look at it, actually is already balanced, so we don't have to do any balancing ourselves. And we also need to include our state symbols to know which species are going to break down into their ions. So the sodium carbonate would be a solution, that's aqueous. The sulfuric acid would also be a solution, aqueous. The sodium sulfate we produce, that's an ionic solid, but in aqueous solution, it would be dissolved up. And then we have CO2, which is a gas, and water, which is a liquid. So remember, anything that's aqueous, we break down into its ions. So we have 2 sodium ions, and a carbonate, 2- anion, 2 protons, and then a sulfate, 2- anion. And then on the other side, 2 sodium ions, a sulfate ion, and then we leave the CO2 and the H2O untouched. Then we cancel out things that are on both sides, what we call the spectator ions. So we have 2 sodium ions on both sides, and we have our sulfate anions on both sides. And so our ionic equation ends up breaking down to be CO3 2-, the carbonate anion, plus 2H+, 2 protons, going to carbon dioxide and water. And so this is the simplest reaction we have. This is a normal reaction. You probably realise this to be an acid plus carbonate reaction. We know that gives carbon dioxide, water, and a salt. But the very simplest form of this is to say that the carbonate anion reacts with protons to produce CO2 and water. Everything else is a spectator ion. Then, to calculate the atom economy, if the desired product was the sodium sulfate, remember that atom economy is our molecular mass of the desired product divided by the sum of the molecular masses of our reactants. Now, when we do this, remember that our molecular masses are just the sum of the atomic masses of all the elements involved. So I won't go through that specifically, but when we add them all up and then do the calculation, times it by 100, and we get that our percentage atom economy is 69.6%. Question 3 was to say that if 9.7 grams of sodium carbonate was used, what's the theoretical 100% yield? So 9.7 grams of sodium carbonate, we can work out the moles using mass over mR. We need to calculate the mR of sodium carbonate by adding up the atomic masses. So we have to have 2 times our sodium, 23, carbon 12, and 3 times the oxygen, 16. Adding all those up gives us an MR of 106.0. So then the moles is the mass divided by that, which gives 0.0915 moles. We then go to look at our mole ratio, and we can see that 1 mole of sulfuric acid reacts with 1 mole of sodium carbonate to give 1 mole of sodium sulfate. So everything's in a 1-to-1 ratio. So therefore, the moles of sodium sulfate are exactly the same. And then to work out the mass, we have to do our moles times our MR. We're just rearranging the equation. Moles is mass over MR. Therefore, if we times both sides by MR, we get that mass is equal to the moles times MR. So we do 0.0915 multiplied by the MR of sodium sulfate. Again, we'll have to work this out by adding up all the atomic weights. If you do that, it's 142.0. And this gives our answer as 13.0 grams. Again, we have to be really careful with our significant figures. We have 9.70 for grams, 3 significant figures, and therefore we give this 3 significant figures. And then finally, in reality, if only 4.3 grams of it was produced, what is the percentage yield? So the percentage yield, remember, is the actual how much product we get. The atom economy was just the theoretical idea of how many atoms were wasted. And so our percentage yield is our actual mass, 4.3, divided by our theoretical 100% mass, which we've just worked out to be 13, times it by 100, and we can see that we get a really pretty low percentage yield here of 33%. Now, because the best way to do this is to do lots and lots of questions, here are 2 more questions with multiple parts. I won't read them all out, but if you want to have a go, pause the video and have a go at the questions, and then the answers will be on the next slide. So the first question was we were reacting magnesium carbonate with HCl to produce magnesium chloride, water and carbon dioxide. This again is an acid plus carbonate reaction, and the question already balanced this for us, but it's always good to just double check for yourself that it's balanced, and it is. So we were told that we had a certain amount of HCl was added to 1.25 grams of impure magnesium carbonate. Some acid was left unreacted. The unreacted acid required a certain amount of sodium hydroxide for a complete reaction. Now, in this case, the question has broken this up into lots of little parts. Sometimes exam questions won't, they'll just give you that and ask you to do sort of the final bit of the question. But it's always good to kind of do it step by step, even when you're working it out, even if the question hasn't asked you to, just to kind of keep on top of everything. So the first task it asks us to do is to calculate the moles of HCl in 75 centimeters cubed of a 0.5 mole per decimeter cubed solution. So this is a simple solution moles calculation. Even if this question necessarily wasn't given to us, this is probably the first thing we do, because from the question we have the concentration and the volume of the HCl. And so we do our concentration times our volume. Remember that we have to convert our volume from centimeters cubed into decimeters cubed, so divide by 1,000. And this gives us the moles of 0.0375 moles of original HCl that we used. The next question asks us to calculate the number of moles of sodium hydroxide that we used to neutralise the unreacted acid. It's always very useful just to write an equation out for this as well. So HCl plus NaOH goes to NaCl plus water. A standard acid plus base gives salt plus water neutralisation reaction. And again, we do the same kind of solution moles calculation, N equals C times V, to end up with 0.0108 moles of sodium hydroxide. And that was the amount used to neutralise the excess acid. So question C then asks us to show that the number of moles of HCl that reacted with the magnesium carbonate was 0.0267. And the way that we do this is to say, well, okay, the original HCl that we added was 0.0375 moles. The amount that was left, i.e. the amount that was unreacted, had to be neutralised by the sodium hydroxide, was 0.0108. So we do one minus the other, which is 0.0267, and that was how much must have reacted with the magnesium carbonate. And then question D is to calculate the number of moles and the mass of the magnesium carbonate, and hence deduce the percentage by mass. So we know that 0.267 moles of HCl reacted with the magnesium carbonate, but we have to look at our equation and see that it is a 1 to 2 mole ratio. So actually the amount of moles of the magnesium carbonate that reacted are half the amount of moles of the HCl that reacted. So we have 0.0134 moles of magnesium carbonate. Then we've worked out the moles, we now want to work out the mass of magnesium carbonate. And so we use our moles with mass over mR, now our solid moles essentially, and we rearrange to find the mass, which is the mR times the moles. And so the mass, we have to have the mR of magnesium carbonate, which we can work out by adding together all the atomic masses. Remember, to give it to one decimal place, it comes out to be 84.3. Times it by the moles, and we get 1.125 grams of magnesium carbonate. Now, if you remember from the start of the question, it said that we had 1.25 grams of impure magnesium carbonate. So there are also some impurities in there that aren't magnesium carbonate. So to work out the percentage by mass, it's very similar to a kind of percentage yield, where we take our actual mass divided by the theoretical mass. The percentage by mass is taking the true mass that we've just worked out and dividing it by what the impure mass is. Essentially, we're saying how much of that original magnesium carbonate that we added is actually true magnesium carbonate, pure magnesium carbonate. So we do 1.125 divided by 1.25 times 100, and that's 90%. So 90% of the magnesium carbonate that was impure we added is actually pure magnesium carbonate. So then the second question, it's a very similar type of question. We have some ammonium sulfate that reacts with sodium hydroxide, which is in excess. This produces ammonia, sodium sulfate, and water. And then we're told that the unreacted sodium hydroxide required a certain amount of HCl in order to be reacted, to be neutralised fully. So the first question asked us to work out the moles of the original sodium hydroxide, and even if this wasn't given to us in the question, it would be a good idea to do, because the data in the question was for the sodium hydroxide originally, so use the data somehow, even if you're unsure what to do. So we're going to do N equals C times V, the standard solution moles calculation, remembering to divide by 1,000 in order to turn our volume that was in centimetres cubed into a decimeters cubed volume, because we have a concentration in moles per decimeter cubed. And so we put these numbers in and we get 0.05 moles of sodium hydroxide. We're then asked to work out the moles of the HCl that we've added to neutralise that excess sodium hydroxide. Again, same kind of calculation, the solution moles, we take the concentration times the volume. Remember to convert the volume into decimeters cubed, and we get 0.0164 moles of HCl that had to be added. Now question C asked us to deduce the number of moles of unreacted NaOH that was neutralised by the HCl. Well, it's a 1-to-1 ratio for neutralisation. Again, you can work out the equation HCl plus NaOH goes to NaCl plus water, a standard neutralisation reaction, and because it's a 1-to-1 ratio, there must have been 0.0164 moles of the sodium hydroxide that remained, just the same amount of the HCl that we used to neutralise it. Question D then said to calculate the number of moles of the sodium hydroxide that actually reacted with the ammonium sulfate. So similar to the previous question, we're going to take the moles that we started with, the sodium hydroxide, the 0.05. We're going to take away the amount of moles that were left, essentially, that were left unreacted, which was 0.0164. And so we have 0.0336 moles of sodium hydroxide that ended up actually reacting with the ammonium sulfate. And then part E was to calculate the moles and the mass of the ammonium sulfate in the sample. We have to go back to our mole ratios here. And so 2 moles of sodium hydroxide react with 1 mole of the ammonium sulfate. So the moles of ammonium sulfate must be half the amount of the sodium hydroxide that reacted. And so we take half of the moles in the previous question, which is 0.0168 moles. And then we have our moles is equal to mass over mR. So our mass must be moles times mR. And so the mass is the 0.0168 moles multiplied by the 132.1, which is the molecular mass of this ammonium sulfate. Again, it's just found from adding up all of the atomic weights. And we end up with a mass of 2.2 grams. And again, watch the significant figures. Everything in the question was to 3 significant figures, so we give it to 3 significant figures, 2.2 grams. So thank you for watching this video. I hope you find it useful. You can find lots more videos like this on my YouTube channel. If you have found it helpful, please consider leaving a review on one of the tuition websites. I offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can always feel free to drop me an email. I'll be happy to help.